So, Kalena, we were talking about Austin, just to let you know before we came into class, and what we were saying is like I was like, I was saying, oh, Austin's a really cool guy. I was talking about Austin. I was saying Austin's a really cool guy, and then Brandon's like, yeah, he's so cool, but he needs to shut up about physics. I mean, like seriously, he talks about it like so much, and then I say, well, he's excited about it. And then they say, well, what was Austin like before? Did you know him before? And I was like, yeah, I know him before. He he was not the best at math at all.
That's really weird.
And now he's killer at math. He's just, and so that's what Austin was like before. He wasn't very good at math. Give me a second, and let's get this party started. And oops, I archived that conversation. But what I want to start our class off with is actually some trigonometry. In fact, some trigonometry that I'm learning from a student today named Breland, sitting right next to me. I'm not learning this trigonometry, but what I'm doing is I'm learning the problems that she's doing. So hang out with me, Breland, for just a second.
Alright.
I'm going to teach class, I'm going to share my desktop, and we'll get this party started. So it's going to take about another 2 minutes, but my thoughts are I'm going to take a little bit longer on chapter 19. I'm still not going to finish it in just this lecture. I think I'm going to need at least till Wednesday to finish it. I'm going to push all the homework back just a little bit, but that doesn't push us too far off schedule. That just pushes us a day back. Cool?
I noticed that there was no Dropbox for this week.
You know what? I made it so that it's, if you look at it says Dropbox assignments for week blah blah blah. You're right. I should put up another Dropbox, and then I'll say, and then what I'll do is I'm only going to put up one Dropbox, and then you guys can put all your assignments in there. Does that make sense?
Oh, yeah. Can you actually see it before we hit submit the final marking?
Can you see it before you submit? What are you talking about?
Because like when you submit it, there's another button for final submissions.
Oh,
After that, you can't edit it anymore.
yeah. I want you to submit it. Give me a second. My wife is calling me. I'm gonna talk to her for just a second while I get this thing set up. Are we cool?
Cool.
Okay.
All right. Hello.
Hi, Daddy.
Hey, I'm in class right now, but I can talk for just a second. What's going on?
Okay, just call me after you're done.
Okay, I will be finished at 12 o'clock.
Okay.
Did Ben go to class today?
Oh, no.
Okay, all right. All right, talk to you later.
Okay.
Love you, bye. All right, folks. Can you see my computer screen? And you can see my stuff. I want to talk to you guys real quickly about some stuff. Who's in trigonometry? Is anyone in trigonometry currently? Deja?
No.
I know Asia is. And Asia's in our class. She should be sitting next to me because she has PA.
Yeah.
And Austin also should be. But apparently the traffic was bad, right? That's what's going on, Brandy? Traffic sucks, Brandy?
Oh, it's traffic bad. I don't know. I took the bus at like 7 o'clock.
All right, yeah. So apparently traffic sucks. That's why, that's why all these people are having trouble coming
No
in.
traffic.
But anyway,
Just like it.
if you're in trigonometry, which is what, Mr. Loving's class?
Yeah.
You guys are learning this, right? You guys are learning, if I don't know, you had the height of a building is 85, and you had the length of the shadow is the 80 times the square root of 3. What is theta?
Yeah.
Right?
Yeah.
Like, this is exactly what I taught you guys on Wednesday. This is exactly what I taught you guys on Wednesday. Actually, it's not exactly, because we didn't really cover the tangent of theta is equal to opposite over adjacent. But we talked about it, right? Right? We talked about how this trig function breaks it up, this triangle up, and we can figure out the angle, and we can figure out the sides and all of that kind of stuff. Like, check this out. Like, this was a straight up problem from the homework in trigonometry. So if you're in Mr. Loving's trigonometry class, say thank you, Mr. Daldy, because Mr. Daldy is going to do one of your homework problems for you. Help me get it right. It was, you got a triangle, and you want to figure, and this is 28, and this was 45, and you want to figure out what this is, which they called it y and they called it x. Actually, I think they called this x and this called it y, which is totally backwards. I don't know why mathematicians think backwards, but whatever. How do you figure out what y is?
Well, you want the opposite hypotenuse, so that would be close.
Right.
Sine, cosine, tangent.
We have angle, which is theta. We have this side right here, which is the opposite side. And we have this side right here, which is 28, which is the hypotenuse. So we would use sine of theta. Sine of 45 degrees is equal to the
Y over 28.
y divided by 28. Are we cool?
Yeah.
And then what I do is I say, okay, y is equal to 28 sine of 45. I want to get rid of that 28 in the bottom, multiply both sides. We're cool with that, Deja?
Yeah.
Yeah,
I
awesome.
get it.
Awesome, good. And the context that we talked about it on Wednesday, we were talking about breaking a force into its components. In this case, what we're doing is we're breaking 28 into its vertical and horizontal parts.
Yeah.
Does that make sense? So that's exactly what we're doing. This is seriously homework straight from the homework assignment that was assigned in trigonometry from Mr. Carlton Loving. Mr. Loving. Yeah, Mr. Lovins. He's a cool guy. I like him a lot. But I mean, this was straight up his homework assignment. So what I'm trying to get at here is the stuff I taught you is totally relevant. In fact, hopefully, if you haven't taken trigonometry, then you're not going to be afraid of trigonometry. Because hopefully, if you learned it in physics, you would have remembered it
Hopefully.
when you learned trigonometry. And I say that with a big
Operative word.
Yeah, I know.
Operative word being hopefully.
Operative word being hopefully, yes, true that, because essentially that's why a former student of mine came in to get help because they didn't remember. So I'm just saying, yeah.
Remember, like,
There.
oh.
Anyway, am I being mean?
No, I
I'm not
remembered it. I remembered it eventually, you know.
Yeah, all right, fine. But I'm not being mean as a person. No. All right, good, cool. All right, so what we're going to talk about is we're gonna tie more into that to that breaking down forces, and bear in mind that I really feel like the hardest part of this class is understanding that concept. I think that if you understand that concept, it's going to help you out with a whole field of trig, but it will also help you out. Like, if you understand this now, then when you take physics, because all of the people that I'm talking to right now haven't taken physics yet.
Oh, if they understand this now, then they'll be like free for the rest of
Yeah. All right. Here, I want you to hear it from a student. Oh shoot! I ended the call. Hold on.
Welcome to WebEx. Please enter your access code or meeting number.
Elevator music.
Please enter. Welcome to WebEx. You will now be placed into the conference.
Sorry, my audio dropped. But what I'm saying is,
Yeah.
can you guys hear me? All right.
Yeah.
I want you to hear it from a former student, like just straight up. And I know that Austin always tells you guys this, and I'm sure Kalena, you hear it too. You're like, just oh my gosh, stop talking to me, because that's what Brandy just told me, that she's like, I like Austin, but you just stop talking about physics. And I'm sure that Tiger would tell you the same thing, but I'm gonna let Breland tell you. Go.
If you learn this now, then like the rest of your math and science and physics and everything will be so easy.
Yeah.
Because this concept is carried on through the rest of your life.
Yeah, I know. You're gonna see this thing until you're sick of it.
Yeah.
In fact, you were sick of it like 5 minutes after I taught it to you.
Yeah.
But I think what I did was, I don't know, I took longer to teach it to you guys. I spent like 2 weeks on that concept, whereas with these guys, I spent like an hour with them this past Wednesday, 2 days ago. I don't know, I feel like I did a better job teaching it to these guys. Like just wading into that concept. I don't know, Kalena and Deja and Victor, did you guys get it when I introduced it to you?
I got about 4, but
Oh, yeah, okay, fine. You understand. I knew it already. Right. All right.
I'm sorry.
But Deja, I mean, since you're brand new to this, is this like...
You
Yeah.
explained it really clearly.
All right. I just want to make sure. Anyway, what we're going to do is...
Am I done here?
Yeah, you're done here. You can go.
Please.
Alright, check this out. What we're going to do here is we're talking about, we talked about the force. And we've only covered one equation, which is force equals k q1 q2 over r squared. Now what we're going to talk about is this thing called an electric field. And the electric field is totally related to the force. In fact, it's saying that your force is equal to E times Q0, or your electric field, which is what I'm going to introduce you now, is equal to the force divided by Q0. And what is Q0? Q0 is like a charge, but it's what we call a test charge. So what we're going to do is we're going to put, like, imagine a particle right here, and it's a charged particle, it's positive Q. Got it? And we're going to take another test charge and we're going to put it over here. This will be Q naught. It's also positive. How would that thing move?
Zero?
No, it would. How would it move with that other positive charge there?
Move apart.
It would move that way, right? And if I plug in another test charge right here, Q0, that would move out that way. And all these test charges, by the test charges I mean I'm going to place these little things out here that I want to see where they'll move. And then that will kind of tell me what the electric field is. We cool with that? Alright, so write down this equation. This equation is the equation for an electric field. It's the definition of an electric field. The Q naught is a test charge. And we're talking about a test charge as a very, very small charge. Because if I had a super massive test charge, then the test charge would actually move my original particle, and that's not what I want. You know what I mean? Like if I said, okay, I'm going to place a test charge, and here's the test charge. Here's the particle. The test charge is totally going to affect the particle. I want to see what the particle has an effect on the test charge, not the effect that the...
Not the other way around.
Yeah, not the other way around. Because, you guys understand? So when we're talking about a test charge, we're talking about one that's so small that it doesn't really create significant force on other charges. It's really just is affected by stuff. We're talking about these theoretical point masses, which is basically like, imagine if you took a mass and you shrunk it down to the size of a point, because that's the easiest stuff to talk about. All right, so if we know the electric field, so vice versa, if we know what the electric field is, then we could nicely calculate out what the force would be in that scenario. So here's, actually, you know what? I'm going to jump a little bit around on this thing, on this topic right here. Let's pretend this. Let's say we have a particle right here, and it's got a positive Q charge right here. Cool? And I have a negative particle right here, and it's got negative Q charge. Are we good with that?
Yeah.
Now I'm going to place a test charge right here. And this test charge is a positive test charge. Q naught is positive. What is going to happen to that guy?
It's going to go away from the positive towards the negative.
Yeah, it's going to go like that. If I draw an arrow, it would be an arrow that looks kind of like that. You guys agree?
Yep.
All right, cool. What about right here? If I put my test charge up there, from the positive one, it would feel a repulsive force going like that. Do you agree?
Yeah.
From the negative one, it would feel an attractive force pulling it towards there. And so the overall force it would feel is something like that. Do you agree? You see what I mean? But if it moves a little bit, like right here, then it's actually going to be attracted more to this thing than to that, and then be repelled by that thing. So essentially, it would move in this path. right here. You guys see what I mean?
Yeah.
Mm-hmm.
Same with a particle or a test charge following like this. And I can even do this. When it comes out here, have you guys ever seen a picture that looks kind of like that?
Yeah.
Yeah.
That's what we're doing is we're kind of providing like a map. It's kind of like a contour map. Like you guys ever see a contour map on a like a regular map and it tells you like the elevations?
Oh yeah.
Yeah.
With what's squinting and everything.
Yeah, or like a not climate map but elevation map where they maybe make it in different colors or whatever and they put these little contour lines and that kind of stuff. And you can imagine in your head that if you put a marble over there, this is how it would roll. Right?
Yeah.
And then if we had like the lines that are really close together, like say here's a contour map, but we have the lines like really close together like this, you know that there's a sudden drop like right over here. I don't know. Let me see if I can pull up a picture. And I'm kind of teaching this off the top of my head, so I get to kind of go how I want. By the way, Victor, how come you're not here? Don't you guys have PA?
Yeah, we'll drive down.
Oh, that's right.
Right after class.
I finish at 12. Your PA starts at 12:30. That's right.
Yeah, so we have a 30-minute time gap to just get out of the house and get down there.
Yeah, but you live close, right?
No.
Oh,
I live
okay.
what? It's all late.
All right. Well, you live 30 minutes away. That's for sure.
Not too bad.
I don't know why my computer is slowing down, but give me a second. Jeez, come on. All right. Sorry. One more time. There we go.
Contour maps.
All right. A contour map. Have you seen something like this? You've seen this before, right?
Yeah.
And then see these lines that are really close to each other? What does that mean?
There's a lot of change there.
Yeah, that means it's really steep right there. Like this is probably like, I'm guessing that this point right here is probably the top of the mountain. Right? You guys see what I mean? So what we're doing here is, and how could we have created a contour map? Well, what we could have done is we could have taken a marble and roll, like let it, or take a wheel or something like that, and let it roll down the hill, and depending on how fast it rolls, will tell us, how closely to draw our lines, our thing, right? Does that make sense to you? So that's exactly what we're doing with this electricity here. Is we're taking and that wheel would be our test object. That's what we're doing with electricity here. We're putting in test charges, and we're saying, let's build a map to see how things would move between these two particles. And if you have a map, because you have the electric field, and you can say, okay, this is how the electric field acts, then you could tell me, hey, give me a particle, and I'll tell you how it will move in that electric field. Does that make sense? So if you knew the electric field, you could figure out the force that happens when it's on there. So like they gave you a few example problems, which I think are actually pretty cool. Let's do one. Let's see. Page 63. This. All right, here we go. Say that we have an electric field that has a magnitude of. Oh wait. Erase. say that we have an electric field that has a magnitude of 4.6 times 10 to the fourth Newton coulombs. That's my electric field. And I want to figure out what force is acting on it if I use a charge that has positive 2.80 microcoulombs. Well, all I do to figure out the force is I just multiply this times this. So that would be 4.6 times 10 to the fourth newtons
I'm late.
per
sorry.
coulombs. What's up, Asia?
Hi.
All right.
So that's the force of the electric field on the test charge.
No, yes, this is the force of the electric. No, this is the force that the electric field provides to this charge, and it's not a test charge anymore. This is a regular charge.
Oh, yeah.
And then you multiply that by the 2.8 times 10 to the negative 6 coulombs. I put 10 to the negative 6 because the coulombs comes out with the coulombs, and therefore we have, I don't know, what, just plug that into your calculator, whatever you get. I think it's 0.129 newtons. And that's your force. So that's the force that would act on that. Are we cool with that?
Yeah.
All right. By the way, Asia just came in. Traffic?
Yeah.
Yeah, that's what I was told. You smell nice.
Me?
Yeah.
Thanks.
You're in Trig.
Yeah.
You're in Mr. Loving's Trig. I was helping a student with Mr. Loving's class, and they were showing me this is what your homework was. Did you do your homework?
Yeah, I didn't.
All right. And then what I was noticing is like your homework was if this is 28 and that's 45, then find y. But that is like exactly what I taught you on Wednesday. So what it was like.
It was easy when you were teaching. It was only I know that.
Oh, okay. So you learned this before I taught it, and then when I was
Yeah.
teaching to you, you're like, oh, dude, I already got that.
Yeah.
Good. Awesome. Because if you learn this now, you're gonna kill hopefully this class and other stuff. All I did while I taught you, or what I taught while I was gone, is that I'm introducing a new thing called the electric field. And the electric, because all we did was cover forces so far. We said force is equal to kq1 q2 over r squared. Now I'm going to talk about electric field, which we're defining as just you take that force and you divide it by q naught, and that would tell you how the electric field is going to be set up. So when you have two particles, there's an actual electric field that's set up. And actually, I think I can even show you a picture of this. And it actually looks pretty cool. Electric field, two particles, two point charges. Let's do that. See, look, that's the picture I drew. And you guys are like, whoop-de-doo, you know, here's this theoretical thing that you have. And I'm saying, no, it's not a theoretical thing. Let me look up the word nails. There we go. No, that's not what I want. I want actual nails. Or let's look at magnetic shavings. Oh, awesome. Look, this is craziness. Here's a bar magnet. And that bar magnet has a positive and a negative pole. And look, they took pieces of a magnet, and they took the shavings and they put it all over the place. And then they just put the magnet down, and this is the configuration that those shavings made. The shavings align themselves with the electric field. And look what it did. It kind of leaves the north side and like curves into the south side. Are we cool with that? Is that kind of crazy? That's exactly the picture I drew right there. If I had this as a bar magnet. Like, this is real stuff, dudes and dude girls. I just think that that's awesome. All right, anyway. And we talked about how an electric field can actually be superimposed. Well, we haven't talked about that, but I'm letting you know now that, well, let's talk about this one. If we're talking about a point charge, we're talking about like a charge that is just a plus charge particle over here, and we have a test charge. The electric field will always radiate outwards, towards, you know. If you're just talking about one particle, it's just going to move away. That picture won't look interesting. If you have two particles, then it will move, you know, it will move kind of like in this shape. If I had two positive particles, like a positive Q and a positive Q, how would that electric field look? I'm just curious to know if you know. All right, so let's try a test particle. Let's put a test particle right here. What would happen to it?
It would go like straight up.
It would go kind of like up, like that. It would actually kind of look up and away, right? Because if you're talking about a particle right here, it would be being pushed away from that positive charge, but it's also pushed away from that positive charge, giving it kind of a overall effect of being pushed in that direction. We cool? But check this out. So what would a particle over here do?
Go up-ish.
It would go up-ish, kind of like that. In fact, they would all kind of go away from each other. We cool?
Okay.
All right, check this out. Let's see if we can look up a picture on that one. Electric field, two positive particles. Electric, two positive charges. There we go. This is the electric field of two positive charges. That's what we drew. Pretty cool, huh?
Yay!
Yeah, and actually, you know what? This I'm not saying that like this is just pictures that we draw. Let's look at metal shavings. When we put, like, look, this is what it physically is. When we actually put the plates down, here's equal charges. Look how they kind of diverge from each other. I know it's hard to see. Let me see if I can get a better picture. I want actual metal shavings. Okay, this is positive, negative. That's got to be positive. All right, this is what we're saying about a positive one just shoots everything straight outwards, radially outwards. But two positive ones. Okay, wait. There's actually pictures of these things. I don't know why it's so hard for me to find. It's usually because the pictures aren't very, like, it's hard to see it. If I actually had the thing, I could show it to you with those metal shavings. And you guys seen those metal shavings before, right? You guys actually saw like they actually have like those Etch-a-Sketch things or something like that, or it picks up the magnetic pieces. Yeah, if I had one of those, I put two positive charges. This is how they would align, and it's crazy, and it's cool, and I like it, and so deal with it. Yeah, I think that other picture is the best one we got. But anyway, you kind of see what I'm getting at here. Cool? All right. So these things can actually be superimposed. That's kind of what we're talking about here. Now, we got a bunch of example problems. I'm going to finish that. And you know what? I didn't think I was going to finish the whole lecture today, but I might. I might actually get through with this whole thing. So we got electric field on a point charge. Oh, okay. Okay, this is section 4.4. Alright, here we go. Electric field lines. This is section. Let's do that. Superposition. Got it. Alright, cool. Let's finish off 19.4. The center region. Give me a second. Find out where I'm talking about. Alright, here we go. Find the electric field of a point produced by 1 microcoulomb point charge at a distance of 0.75 meters and then 0.5 meters. Okay, fine. So you got a charge that has a positive 1 microcoulomb. That would be 1 times 10 to the negative 6 coulombs point charge, and you want to figure out what the electric field is produced if you're standing 0.75 meters away. Cool? So what we would do is, okay, by the way, I think I forgot to tell, I didn't write this equation down, but if this is the case, if the electric field is the force divided by the test charge, right? And the force between these two charges is Q naught over R squared. I put a Q naught over there because that's my second charge.
What does that mean?
Q naught is your Q0 would be what I'm calling a test charge.
Oh, so that's
The way we're building these kinds of things, and I kind of like this analogy that I use, is have you ever seen a contour map?
I don't think so.
If I show you a contour map, you're going to be like, dude, I totally seen a contour map. Are you kidding me? All right.
Didn't you just show it? Show us
I did, but Asia's here and she's asking me questions. I want to show her to her, and I'm sorry if I'm going a little slow. All right, you seen something like that before?
Oh, yeah.
Yeah, and you're like, dude, I've seen that. I got that, right? Like that's nothing new to me. And this kind of shows you elevation, that kind of stuff, and it doesn't actually show you the actual height or an actual like thing in there and how it moves, but you can kind of guess that if I were to put a tire somewhere over here, I could see how that would move. If I put a tire right on that X, how would it move?
I don't know exactly.
Question to the class. If I put a tire right on that X in that picture, how would that move?
right on the X, it would stay still.
I don't think it would
Yes.
move. Because it looks to me like that's a flat area. You guys agree? Now, see the number 5,000 over there? Or maybe 5,100 over here? If I put a tire over there, how would that move?
It
It would
would
roll down.
That would shoot down this direction, right?
Okay.
So what we're doing is, and in order to maybe in order to build this map, we would bring it along with us. We would go to the cliff and we'd bring along with us a tire, and we would say, okay, we'll put the tire here. If it rolls real fast, we'll put those lines close together. If it rolls real slow, we'll put those lines far apart. If it doesn't move at all, we'll say that that's flat. You see what I mean? We'll bring along this test tire with us. Well, that's what we're doing with electricity. We're saying, okay, I have two particles. I'm going to throw in a test charge, and this test charge is not big enough to actually like affect things. It's just big enough to be affected by all of these things. And so if I put a test charge here, it would kind of go this way, because I know that it goes away from the positive and towards the negative. That's why the bar magnet made that picture. And then what I say is, all right, now I have a bunch of these test charges, and I throw them all over the place, and I can see what the map is. I've made a map, right? So now after I have the map, you could give me a tire, and I could tell you how that thing will move. You could give me a charge, and I can tell you how that thing will move. So in the first thing, this equation right here, we defined, okay, here's how to construct our map. This is called our map. Our contour map for this thing is called an electric field. Our electric field is defined by the force divided by the charge. It's kind of like saying the force divided by, or like the acceleration that's going to happen on that field or on that cliff is equal to the force that it experienced divided by the mass. You know what I mean? In fact, it's exactly like saying that. This is like the same analogy back to F equals ma. Have you seen F equals ma before in your lifetimes?
Yes.
Victor says yes. Have you seen it? You haven't even taken. Or most people who haven't even taken physics have seen this. And all this is back when I taught like force equals mass times acceleration. I'm sure that you guys have seen this before.
Probably have, just don't
Like I taught it to my 8th graders. I taught it to them in 6th grade. I'm going to continue to teach it to them in physics. But anyway, this is basically the way we're going about that. And so here's what I'm saying here is if we have only 1 point charge
Put that on the bottom.
and we throw in a test charge, then the force between them is going to be this, right? And the electric field is going to be set up like this. Do you agree? So I'm going to take this and I'm plugging it in here, and then my electric field is really KQ over R squared.
Okay.
Right? Because
Yes.
all I do is to get my electric field, I just divide by Q naught. Those cancel out, and so I get KQ over R squared. So if I want to do this problem, it's very simple. All I got to do is if I want to figure out the electric field 0.75 meters away, I just take the K, the Q, and the distance squared, plug into my calculator, and voila, I have my answer. K is 8 times 10 to the, actually, K is 9 times 10 to the 9th power, Newton meters squared per coulomb. Q is the charge that they gave me, which was 1 times 10 to the negative 6 coulombs, divided by your distance squared, which is 0.75 meters squared. So this becomes 1.6 times 10 to the 4th newtons per coulomb. Are we cool? And how would I plug in 1.5 meters? Well, I would just change the R. Boom. Deal with it. You see what I mean? And when we're making these, electric field drawings, and actually I was planning on covering that later, but I might even be able to just finish it off now. When we're making these electric field drawings, essentially we're building those contour maps. So if you understood the analogy I made with the contour map, this should be pretty straightforward for you. But anyway, let's talk about this, the superposition of two fields. And I think that, you know what, I think that this would be a good one to talk about. Let's do it. So I don't want to do this problem. I want to do another one. Let's do this one. No, this is the same exact problem as before. Let's do something else. What was your... Let me see if I can do a homework problem or something close to it. All right, 1 second. Sorry, folks. I don't like the example problem that I came up with because it just seems too easy to me. Well, all right, whatever. Let's check this out. I'm not going to finish off this example problem because this example problem is straight out of your book. You can read it on page 668 and have fun with it. But here's what I'm saying is two charges, each equaling 2.9 microcoulombs, is placed at the corners of a square. Got it. So charge 1, charge 2, they're both positive 2.9 times 10 to the negative 6 coulombs. Cool? And the square that I'm making is a 5 meter or half a meter square each. We good?
Yeah.
Find the magnitude and direction of the third charge in the sketch of the electric field of the third charge. Okay. Well, the electric field from here is straight this way, right? And that's equal to, E is equal to KQ over R squared. And the electric charge from here, or electric field from here, is going to be smaller because R is going to be a bigger number. So it'd be E2 is equal to KQ over R squared. But these are different R's. So this would be R2 and this would be R1. Are we cool? And guess what? In order to figure out what their total electric field is, do you know how to do that already? Yes, you do. You can take this one, you know the angle that it's at, right? Because that's the same as this angle, which is a 45-degree angle. You can break that guy into its components, right? And then you can take this guy and add him to that, and then you say, okay, well, this plus that is equal to that, which is that. It's exactly what we did on Wednesday. In fact, it's almost so like the same problem that it's exactly the same problem. The only difference is we divided by Q naught.
Right here.
And that's not even that hard. We actually talked to you about you at the beginning of the class.
We did?
Yeah, we did. We talked about
Is
Austin.
that how he lifts weights?
Oh, excuse me, lift weights. Ooh, excuse me.
Mr. Valdez.
Yo,
Mr. Valdez.
yes, I'm listening.
So, is this calculating the electric field or the charge on that point?
Since we're using this equation KQ over R squared, we're calculating this thing called the electric field. The electric field is totally related to the force. But you know, I mean, it's just now we're talking about the electric field. I think when you look at this lecture, you're going to be like, "Oh snap! I know that." Like, essentially, I'm introducing F equals ma.
Oh, I love that equation.
Well, right, but I'm introducing F equals ma to the concept of electric fields.
Only it would be different, right? I mean, just force pushing upon another, right?
Yeah, but we're not talking about. Basically, here, look. I introduced this concept. This is the third time I'm talking about this, but anyway, I introduced this concept of electric field, which is equal to F over Q naught. But if you look at that, F equals EQ naught. Doesn't that look a lot like F equals ma? In this case, this would be the A,
So I just see, yeah.
and this would be the M. That's it. All right. Anyway, 19.5. I didn't even plan on covering it, but hey, let's cover it. Let's finish this off because I actually already did cover it. I'm already done with it. All right. Here's some rules about electric field lines. If we want to draw our contour map when we have two particles, when we have two things that are just like these test particles, here's the rules. There's 4 rules that we have. They always point in the same direction of the field vector at every point. What? Okay, hang with me. Bear with me. Just say, okay. All right. Rule number 2, they start from the positive and they end at where?
So I built the chart already.
They end at the negative,
Oh,
right?
Right.
They start at the positive and they end at the negative. That's both rule 2 and 3. And then rule 4 is they're strong when these field lines are denser, and what I mean by denser is that there's more lines in a given area, then you're talking about a stronger field. So here, let's do this. Let's do positive Q, negative Q, and I just had this picture up here, but for Asia and Austin's sake, who just came in late, let me share with you how it works. If I put a test charge right there, right, how would that guy move? He'd move away from him, closer to him. He would kind of move in this direction, right? Actually, if you were right in between them, he would move completely horizontal. So in essence, the path that he would follow would be something like this. It starts at the positive, it ends at the negative, so it goes in this direction. Got it? And what I mean by it points in the direction of the field vector at every point. The field vector or the force vector would kind of look like that. These arrows point in the same direction. That's what that rule number 1 means.
You're archiving this, right?
I'm archiving this. If I put a test charge right here, how would that guy move? I just drop him in right there. How would he want to move?
Move to the right. Oh,
He would move to the right, right? But then as soon as he gets a little bit closer to the right, he would start moving up towards that guy. And then he would move that towards that guy. So in essence, his path would kind of look like this.
So basically, never go to the positive.
Right, because we're talking about dropping in positive test charges.
Oh, okay.
So if I put another one over here, how would that look?
Where did you put it?
Right down here.
Oh, it would start moving to the right, but then it would get closer.
Kind of like that.
Not much more.
And then the same goes for here, and same goes for here, and same goes for here. And then check this out, because it will blow your mind, Austin. Is when we looked at
I've seen that before.
actual metal shavings and we put it on a magnetic bar. This is what we got.
I've worked with that in chemistry.
That's what we got, which is actually the physical representation of this crazy kind of weird thing that we're talking about with field lines.
So how much test charge did they drop in that?
What is that?
How much test charge did they drop in that? Just
Well, they're not dropping test charges. They took a magnet and they shaved it off.
Mhm.
And then they just took metal shavings and put it on. We figured this out by accident. Basically, when we were making the microwave, they like had a bunch of nails on the table. And then they like had this huge magnetic, these giant magnets that turned on. All of a sudden, the nails like aligned themselves. And then people were like, what the hell? Right? And then they said, okay, here's what must be going on based off of this. They actually saw these nails just kind of go on the table, and all of a sudden, imagine that would be kind of crazy. Like you know, you have a bunch of nails, right, on table, and then like you turn on these magnets, and it kind of like goes, and it makes this picture for you. That would be rad. Do they use the word radical anymore? No.
I've only heard
That would be pretty freaking awesome. And that's what happened. So this is the theory that I'm teaching you guys. So we're creating these electric field lines. If I'm talking about just one charge, the electric field lines pretty much just radiate outwards. All test charges would just kind of go away. If I'm talking about a negative charge, all of the field lines would go inwards. And when I'm drawing a picture, if I have positive Q versus negative 2Q, there would be twice as many lines here as there are here. Why? Because I'm talking about a negative 2 charge on it. So it's twice as dense. You understand? I mean, essentially, this is really just drawing pictures.
Yay.
Yeah, I know. That's awesome, Mr.
I'm
Dalday.
terrible at drawing pictures, by the way.
No, but I mean, it's not even that. You're not even drawing pictures. I'm not asking you to draw a face. I'm asking you to draw 2 points and then draw lines in between them. I can do that. All right, check this out. Here's another one that's kind of crazy. Here's a positive 2Q and a negative Q. Positive 2Q, negative Q. Got it? So obviously the lines are going to go straight this way, right? But let's shoot one straight up. If I shot one, well, if I shot one kind of up, it would kind of go like this, and it would curve around like that. And then it kind of looks like this. And it would go all the way around like this.
It's just because it's more
This
dense
guy
on
would
the
go
first,
all
on the
around.
positive charges, why we would do such radical
But look,
movement.
this right here has twice as many lines as this right here. Even though I'm using the same amount of test particles, it's not twice as many lines. That's a lie, but it's twice as dense as the one on the right. It's because like particles that go out here, they don't just stop. They don't go like, oh, I'm stopped. They actually go like this, and it's just such a big circle that we don't have room on
We just don't draw it.
on the picture. Yeah. So
It's like the one we see with the Earth and the Sun.
yeah, these are magnetic fields of the sun, or electric fields of the sun, and that's really it. And let's see. What else can we talk about? I could talk about dangling thread. I think that would be a good one. But I would have to teach you some. I would have to teach you some physics for that. So maybe I won't necessarily do it.
Physics.
It would be force equals ma.
Oh.
I know you know it, but I just don't really want to get into that just right now. You guys ever hear of a Tesla coil?
Oh yeah.
Have you?
Yeah.
All right, here. Let's see. I think this would be a cool one. Radioactive Tesla. No. Sail Tesla. I think this is pretty cool. Here we go. All right, I'm gonna play some music real quick. It's just real quick.
There's no music.
I know. Give me a second. Hold on. Computer's thinking about not wanting to work. There we are. Let's rock out. Ready?
Sail by A.
Can you hear the music? I know the video's glitchy, but can you hear it? Yeah, don't worry about it, but can you hear the music?
What are these coils making this sound?
Check this out. Listen.
I don't hear anything.
This sounds so familiar.
All right. Where's that sound coming from?
Well, apparently Thor.
Yeah, Thor. No, the sound is actually being generated by the lightning. What you are hearing is a version of thunder. I kid you not. The sound is actually being generated by the coils. And they're just modulating that electric field so that they can kind of generate exactly the sound, thunder, that they want you to hear, and then they have that song. Here, I'll send you the YouTube link because I think it's really cool. Physics. Alright, there we go. Wait. Did you get it? There you go. I don't know. Anyway. I sent you guys the YouTube video in the chat, but I mean, you guys can always just look it up. Sale Tesla coil. Now, how would you protect yourself from this?
Protect myself. The music or the coil?
The coil, the thing.
Wear rubber.
No, check this out. Tesla coil suit.
There's a suit.
Made out of rubber.
There we go. Yes, this is cool. Let's do this.
He's gonna walk into it or something. It's just gonna hit him. Something.
No, they're actually fighting.
No, it's dangerous.
It actually kind of. I've done this before.
Really?
Yes,
You're that's dangerous.
it's rad. It is dangerous. If I didn't have the suit on, you could easily be fried. Like, I mean, there's no question about it. But I don't know. Let me show you because I think it's cool.
Would the electricity actually jump to you if you didn't have the suit on?
Yes, it would go through you.
It would.
Yes.
Oh.
But what we're going to talk about is this thing called a conductor and a Faraday cage. And these electric fields will actually... Okay, wait. Where's the video, dude? Come on. Oh, it's not going to play for us because it's lame. Because it's lame.
Put it in the chat.
All right, hold on. What is the dude from Mythbusters' name? Is Adam Savage, Tesla, Coil. Oh wait, it is playing.
Oh no, it's playing.
Oh no, error occurred. Please try again later. That sucks. You suck, YouTube. All right, Architect.
Yeah, it does.
Adam Savage. Here we go. You guys know Adam Savage, right? Do you guys watch Mythbusters?
The only one you show me is with the bullet.
You should watch
No.
Mythbusters. Do you guys have Netflix?
Yeah.
Watch
No.
Mythbusters.
Yeah.
Watch more Mythbusters. Anyway, Mythbusters is like I think one of my favorite shows. One of them. I'm a nerd though, so I don't know. Man, what's going on, YouTube? You're sucking. All right, here we go. Here we go. So there's some Tesla coils like you just saw. They're actually making lightning. And what is he in?
Box. Some
He's in a box. Is it a super safe box? It has chicken wire on it.
Oh, wow.
That's what it has.
Doesn't matter.
I kid you not. It has chicken wire on it. And they're going to turn this thing on. And it's going to be awesome. Because they're going to turn it on and play AC/DC Back in Black. With the dude in chicken wire on it.
Oh, that's right. I totally remember this now.
Yeah, didn't they did something like this in
A movie.
one of those movies. The Sorcerer's Apprentice.
Yeah. That's what
Oh,
I'm
the
remembering.
Sorcerer's Apprentice.
With
Right.
One Republic.
Right. And they did the do 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 do.
Yeah, that's the one.
Right, and the dude was like this physicist nerd dude, right? Like I was down with that.
Yeah.
I was like, I can relate to that dude. Hey,
He was
I
using
like that
Tesla
guy.
coils to
He was
make
using
the-
Tesla coils, and what was he in? He was in a bird cage.
Yeah.
Like seriously, and like
Yeah.
and the girl was like, "Are we safe in here? This looks like a bird cage." Like seriously, there's chicken wire on the outside.
It is.
And he's like, "Yeah, it's totally safe. I do this all the time. I play with lightning in my
Yeah.
chicken cage." Right? So here's what's going on, okay? Here's what's going on. Alright, so we talk about electric field lines. We can talk about electric field lines on a plate, but I'm going to talk about, gosh, my computer is just acting so slow. I'm going to talk about this thing called a conductor. A conductor is things that, we talked about a conductor. A conductor lets the charges move
Evenly
freely.
spaced. Oh, they evenly space out, right?
Right, and they'll evenly space out. So if I have a ball where the charges are allowed to move freely, then what's going to happen is your electric field is going to come over here, okay? And where is all of these electric field lines going to end at? On the negatives, right? Now,
Okay.
when this Faraday cage has all the negatives pulled over to the left, what happens?
To the.
What happens to the
It goes
positive
right,
charges? All the negatives hang out on the left
Oh, they
side.
go to the right.
Well, the positive charges will go over to the right.
Yeah.
And so the electric field will come out of here. Because they leave the positive side, right? But what happens inside?
It stays even neutral. Right?
It's neutral. So it's
so that whole
zero
that
inside.
cage is just
So
a
it's-
conductor.
inside the cage,
It's neutral.
no electric field.
But on the outside, you
Outside the
charge
cage, you actually have crazy stuff going on.
So basically, the box.
But you're
wire
safe
is a
inside.
conductor.
Yes, the chicken cage box is a conductor that allows you to basically stay inside and be safe. Yeah, have you guys ever noticed that, like, when you guys have your cell phones, you guys go into the elevator, like your cell phone stops working?
No.
Yeah.
Okay, well, I've got cheap cell phone. I've got the one that's just about to die, no battery, flip phone. It almost looks like the one that I'm going to make a call and order drugs on, or like order a hit on somebody and like murder somebody. And then after that, I'm going to take out the SIM card, eat it, and then smash the phone because I don't want the FBI to trace it. That's how ghetto my cell phone is. But when I'm sitting in my office, it's hard for me to make calls. Why is it hard for me to make calls? Because the electric field doesn't really go through this office. And you know why? Not because I'm surrounded by concrete, but because I'm surrounded by actually steel. There are steel beams inside of this thing, and there's like wiring over here, and that wiring messes up the fields. I'm actually inside of a conductor, and some buildings have more steel in it, therefore creating more of this like trap that you can't actually make calls out of and whatever. That's what it is.
Is that when my phone doesn't work in Walmart?
Possibly. Crazy, huh? And now you know. And I think that's where it really was really cool. Actually, I hope that I'm not lying about that, but I think that's, yeah, that's true. So, you have shielding, you have conductors, and we can talk about charging by induction. But I've got 2 minutes left. I'm all done because now I got to end on time because Victor's got to go and I got to grade everything. But why don't you finish reading off chapter 19? I'm going to adjust the homework accordingly. I'm going to give out grades. And you want to know a secret is everyone passes at least, right? I haven't decided how many, I haven't graded as much homework for this class yet because I'm going to make sure you guys did turn in your homework, but for the most part, you guys are going to pass this grade check. Don't worry about it. All right, don't freak out about it. At the very least, the very lowest, you'll get a C if you didn't turn in any homework. Okay? Because you guys have been hanging out with me, you've been talking, you guys have been coming to class. So, hey, I'm letting you guys go. You guys got really a 2-hour break, and then you guys come back at 2 o'clock for STEM class. Right? Right, Deja?
Yeah, I did.
Right, Kalena?
Right.
Right, Victor? Good, and we're going to talk story in that one.
No.
Awesome.
And oh yeah, Victor, you're not in my class. And what we're gonna do with that class is, just to kind of let you know, is we're going to. I'm hitting math pretty heavily in this class, so I'm gonna back off on math in the next in the STEM class for now, just so I can get you guys introduced to it. Cool. All right, talk to you guys later. I got to stop the archive. I'm gonna go. We're done with class. Finish off chapter 19. We are done with this stuff. What's up?
So I drove all the way back
Okay, bye.
to DMV without using my
Yeah,
right
see ya.
mirror.